Good afternoon, everyone. Thank you for joining us today and welcome to the BDTI Skills Studio. Our topic for today's session is an introduction to statistics. As you probably understand from the title for this workshop, it's beginner friendly, so everyone can find it approachable and easy to follow. Now let's have a look on the agenda of today. First, we will provide an introduction to what BDTI is. Following that, we will dive deeper into the workshop content. After the workshop, we will open the floor for Q&A session. And finally, we will wrap up with a summary of today's session. Along the webinar, feel free to share your thoughts, ask questions in the Q&A section. For this, you need to click on the three dots on the right to see the Q&A session. Please be respectful when commenting, and we invite to ask questions relevant to the topic of statistics. We encourage you also to share learnings and don't forget to register for upcoming workshop session. Now I will hand the floor to Maria Claudia, who will provide an overview of BDTI.
Thank you, Aurora, and welcome back. We are very happy and also excited for today's session. And it's about statistics, so it's something very important for our jobs, and it's also very interesting to start learning little by little. So let's just frame it let's say this series of webinar. Our main program behind this workshop is the big data test infrastructures, and many of you already know about this very good opportunity from the European Commission. This infrastructure is basically a free data science playground that is completely based on open source tools for data analytics and, of course, AI and all necessary tasks that you need to perform using public sector data. So basically, the idea behind this program is to offer to public administration that are European, so for example, municipalities, regions, ministries, it doesn't matter if you're big or small, a free infrastructure in the cloud that is already set up and ready to use. So once you have a clear idea in your mind, in your team about processing data in order to achieve a clear objective, for example, answering a business question, maybe try to solve some public good challenges, you can submit your idea and then we can create for you this infrastructure in a very few steps. Just a small comment is about the data you are going to use in this infrastructure. The only condition and the only requirement is that you need to use open data. So we are not allowing personal data usage, and also it doesn't matter if it's just a small data set and it's not a big data set. So if we move to the next slide, here we prepared for you a very nice, let's say, very nice overview about all the tools we are currently offering in this big data test infrastructure. That again, it's a web platform that you can have for free. You can see here the different data journey steps. They are very common when you're trying to approach something with data. So you start from collecting data, processing, analyzing, visualizing, and finally try to share something with your final stakeholders. Maybe they could be citizens, maybe politicians or academics. And based on what you need to do, you have many different tools that you can decide to use. Probably you know some of them, but just a very important information is that all of them are open source. That's why we are focused on this aspect, because after the 6-month period for your pilot project, you can easily move to your environment without facing high costs in terms of licenses and the installation of these tools. So if we move next, let's define one time more the audience for this big data infrastructure. Basically, you need to be a public administration, a European one, and it will be great maybe if you can combine your expertise, it probably is more on the policy side, with some technical expertise, because sometimes public sector is suffering from lacking of technical skills. So that's why we are always proposing a good match between public servants plus maybe students, academics, or people working in the GovTech startups. So we are more than happy to create with you pilots, adding people from academia, maybe some master's students or PhD students, or also people from private companies. But the only mandatory condition is that the submitter needs to be a public sector, let's say, entities. So please follow our initiative. You find a lot of information in our website. And in this slide, we just, we just want to underline some of our last interesting pilots that are currently ongoing. One is from Germany, the other one is from Finland, and the last one is from Naples, Italy. All of them are really, really, I would say, interesting and super cool because they are trying to approach public sector, let's say, challenges from different perspectives. Some of them are more related to machine learning development. The other ones are more related to data analysis and try to also visualizing using some dashboards, some insight, for example, about urban mobility and also about public transportation and in general public services in the different cities. Then I would say that we can move to the next slide. Thank you. And then we can finally start the workshop of today, that it's this amazing introduction to statistics. You will learn a lot, so I will recommend you to stay very focused because this session is going to be very, very dense. I really like the approach we are going to follow because we have a very deep introduction from the theoretical part and then a more practical section using some tools that we are offering in the big data test infrastructure. So thanks a lot for your attention. Also, thanks a lot, Roberto. The floor is yours.
So thank you very much, everybody, and thank you, Maria Claudia, for the introduction, and welcome to this workshop to introduce some basic concepts in statistics. Let's have a look at the agenda for today. In this workshop, you will learn what statistics and why it's needed. Then we can explore some concepts in descriptive statistics and also in probability. And in doing so, we're also going to cover some key measures, key calculations, and have some, let's say, practical demonstration of how you can do these things using NIME Analytics platform. And in the end, we're going to have a little summary just to recap on the most important points. So the first question that we're going to address, or first topic we're going to address, is what is statistic and why it is needed. So first, let's define what statistic is. Statistics is a branch of mathematics that deals with the collection, organization, presentation, analysis, and interpretation of the data. And their goal is to basically make informed decisions, so to basically make sense of the data that we have. And statistics is basically or virtually used in all disciplines. So it's a very versatile discipline that can be used in the social science, in the humanities, in business, or also by government and public entities. And usually, in fact, organizations and governments collect data to then try to basically answer some practical questions. And here I have a little example where a city government, for example, need to understand whether it is more meaningful to open a hospital or maybe a school. And how can they do this? They have to collect obviously information about the people living in a specific area, so where they live and about also their age. And based on this information, so computing statistics about that, they can now finally make an informed decision whether to open a new hospital or a school. But statistics itself is not only the name of the discipline, or let's say the branch of mathematics, but it's also a way to denote the data themselves. In fact, we can talk about economic statistics or financial statistics and so on. But for data to be considered statistics, they must be complying with some requirements. That is, the data must be comparable, so we can establish a comparison between data point A and data point B. They must be representative. This is a very important point. We need to ensure that the data that we are working on are representative of the phenomenon we want to investigate. But it also must be collected in systematic order. So let's say, for example, every second week, every month, or every year. And they need to be obviously also aggregated in a way that it presents some specific facts. So something that is, for example, a percentage or an annual value and so on. And obviously, they need to be collected for a specific planned purpose. It doesn't work just to collect data, and then so any collected data, it's not per se statistics, but it has to comply with these requirements. And why statistics needed? This is a very important question to answer, and the reason is because events and phenomena that we observe in our reality, they tend to vary a lot. And so because they vary a lot, we need to find a way to describe how they vary, understand if there is a general trend, figure out what is usual in the data and what is unusual, what is, let's say, abnormal to a certain extent, and maybe predict if there is some variation in our data. But also because usually when we deal with reality and with the data that we collected to describe a specific phenomenon, we very rarely have a complete picture. So we rarely have a set to describe every single detail of the phenomenon. So we need to be able to deal with uncertainty. And statistics gives us the tool to be able to deal with this uncertainty and still make some informed decisions. So let's now see some key concepts in statistics. So the very first difference I want to make is between a population and a sample. A population, and you can remember it by the P that is underlined here in the slide. Population is a collection of all the items under investigation. It's usually not the case that we work with populations because collecting or encompassing the entire phenomenon fully is rather hard. So usually we don't work with populations. But population in formula, because we still have formulas in statistics to work with population, are usually represented, so the number of items of the size of population is usually represented by a capital N. And whenever we make basically a measure that represents a population, we speak of a parameter. And in fact, think of a population, for example, as you see on the slide, an entire, basically all the letters in the alphabet. So there would be the full picture of the phenomenon we want to study, basically the alphabet. Much more likely, however, it is to work with a sample, basically a subset of the population. And a sample, which is in fact, can be visualized like this, basically a group of all the letters in the alphabet, is usually represented in formulas by a simple n, so that the n represents the sample size. And whenever we compute some measures they represent the sample, they refer to the sample, we're talking about a statistic. So for example, we saw before that economic statistics, so the way to denote the data, so the measure that we compute is usually referring to the sample. But because we do work with samples most of the time, so not with the entire population, we do need to spend a few words about the concept of random sampling. So to abstract the subset of data from the population, we need to implement some random sampling procedure. The basic one, the most simple one, is the simple random sampling procedure. That has to have some sort of requirement. That is to say, each member of the population that is going to be then part of the sample needs to be strictly chosen by chance. It also needs to be equally likely to be chosen, and also all the sample, so basically every possible sample of X amount of items should be equally likely to be chosen. If we respect those let's say, requirement, what we obtain is a random sample. But why do we even need that? Because we want to ensure that the sample we work with, that is representative of the population, is unbiased and is a fair representation. Only in such a way we can make then we can describe, we can infer information about the larger population. So this is why we need a proper sampling procedure. Given that we have now defined, let's say, the two main group of data, the population, the sample, and we realize how we can let's say, sample those data points, think of statistics as having two main branches. The first one is the descriptive statistics, which involve basically the collection organization, summary, and display of data. And each, let's say, and it can be further divided into little points. For example, the collection of those data, which is something we will not engage in this specific webinar because we already have data provided by Eurostat. But we will engage with, let's say, the part of summarization and presentation of the data. And the second branch is that of inferential statistics, which basically involves drawing conclusion or making decision about a population based on the sample results. And here, two main, let's say, tasks usually are estimation and hypothesis testing. So basically testing whether a claim about a population is actually true. Okay, since today's focus is on descriptive statistics in the first part and the second part of probability, let's now dive into descriptive statistics used in this specific section to summarize our dataset. So what is descriptive statistics? Basically, it gives us a basic summary or measures to summarize and to describe our data. Our goal in this case is to understand the data and to present in a much more meaningful way, specifically when we don't know anything about the data. So this is usually the first step we take whenever we import a completely new data set. We don't know anything and we want to understand some key measures. So we want to summarize in a way that give us some key information. And within descriptive statistics, we have different branches, and one is univariate, which is basic univariate analysis, which involves analyzing only one variable. And we also have bivariate analysis, where we compare two variables to determine whether there is some meaningful relationship between them. We even have a multivariate analysis where we analyze the relationship between more than two variables. In today's session, we're going to only focus on the first two. Okay. Speaking about univariate analysis within descriptive statistics, we have different measures that we can compute to describe our data. One of the first, and probably the most common one, are measures of central tendencies. This measure basically describes the whole data set by basically picking one single value that represents the center or the middle of the data. It works with quantitative and qualitative data, and some common examples are the mode, the median, or the mean. Another measure is a family of measures of variability or dispersion. This measure, what they do, they describe how similar or how far away or spread out are basically our observation with respect to a particular data item or value, which usually is the mean. It only works for quantitative data, and popular examples are, for example, the range, the variance, and standard deviation. A third family of measures is that of shape distribution. As the name indicates, they describe the shape, so how it looks like, basically, the distribution of our data within the dataset. And it only applies for quantitative data, and typical measures are skewness and kurtosis. We're now going to have a look at the key measure within each of these three families. So, speaking of measures of central tendency, the first one we're going to cover is the mode. The mode is basically describes the most commonly occurring value in your data set. It has the advantage that it can be used with numerical and categorical data. But however, has let's say the cons that sometimes there might be more than one mode. So we talk about bimode or multi-mode data set. Or if we have a numeric value that has many different values, many different numeric values, we might end up having zero mode. So we cannot compute the mode in that case. So how can we describe, let's say, the central point of the data? Well, we can use, for example, the median. So the median represents the middle value of the distribution of a data set once the values are arranged in descending or descending order. The good point, the pros of using this measure is that it's not affected or is less affected, let's say, by outliers and by skewed data. We will see what skewed data means in a few slides. And it's also preferred in case of non-symmetrical distributions. The cons, however, it only works with numerical data, so we cannot apply to nominal categorical data. The mean, the third measure within the central tendency family, is the sum of all values, so basically of each observation in a data set divided by the number of observations. The good side of it, the good aspect of it, that it can be used with discrete and continuous numerical data. But it is unfortunately much more sensitive to outliers in the dataset and only works usually with numerical data. So what kind of answer can we answer with this measure of central tendency? Well, usually we can, for example, answer what's the mean age in a student classroom, or what is the median income of a country. Or if you want to use the mode on categorical data, we could ask what is the most common pizza choice in Italy, or something like this. Okay. Let's now move to the measures of variability. Remember, these are measures that basically describe how similar or spread out the data are with respect to a specific data value, usually the mean. One of the measures of variability that is worth mentioning is the range. The range is very simply the difference between the smallest value and the largest value in the dataset. And it helps us understand the span of the distribution. That's why it's useful. But on the other hand, it's quite sensitive to outliers. So we need to be using it carefully. But the two probably most famous measures of variability are the variance and the standard deviation. Basically, they provide a summary of how close each observation is from the mean or respect to the mean. So usually, when we have a data set that has basically values that are close to the mean, so they are not so different from the mean, we tend to have small variance or standard deviation. Whereas when there is much more diversity or deviation, so we have values in the data set that are much more spread out, so far away from the mean, we tend to have large variance and standard deviation. And standard deviation, if you wonder exactly what it is and how it differs from variance, is basically variance, the square root of variance. And it is expressed also in the same unit of the data. So it could be kilometers, it could be minutes, it depends what you are analyzing. And therefore, it offers a much more intuitive way to interpret your values. And here, I would like to show you the formulas to compute the population variance and the sample variance. Usually, as you can see in both formula, there are some similarities. Let's start from the population variance. As you can see, that's the symbol here indicates the sum. So it's the sum or the square difference between each value in the population, and mu, the symbol, indicates the population mean. And as I said already in the previous slides, the big N, the capital N, indicates the number of units in the population. For the sample variance, which is however what is most likely that we're going to use, we can basically see some similarity in the formula, with the only difference that this time we're not using observation in the population, but rather observation in the sample. And obviously, this is the mean of the sample, right? And also, again, in the denominator, we use n minus 1. So the number of elements in the sample minus 1, basically to make this estimator unbiased. So this is called degrees of freedom. So the degrees of freedom will allow the data to vary, basically. Okay. And what kind of question can we answer with variability? For example, we could say, what's the income difference between the richest and the poorest person in a country? Or what is the normal, so to say, dog height among your friend's pet? So what is extra large, what is extra small? And using, for example, standard deviation in that sense, allow us to understand how, let's say, what is extra large or what is extra small. Okay. The third family is the measures of shape distribution. One that is very important and popular is skewness. I anticipated a few slides before that we're going to cover this topic as well, the skewness. Skewness basically is a measure that tells us how symmetric or asymmetrical our data is with respect to the mean. And we can, let's say, have some rule of thumb to tell whether the data is symmetrical or a little skewed or highly skewed based on the value. So you see, for example, if the value of skewness is between minus 0.5 or plus 0.5, the data is fairly symmetrical. If it's between minus 1 or minus 0.5, then we can say that data is moderately skewed, and so on. And the second measure is kurtosis. Kurtosis might be a little bit, let's say, unfamiliar. If you haven't, probably maybe you never heard of it. But what it does, kurtosis, is it measure how heavy. You will see in the next slide, next few slides, what exactly means, how heavy the tails of the distribution are or differ from a normal distribution. A normal distribution is usually a distribution that has a very nice bell shape. So it's very, let's say, very clear, very nice, and very symmetric. And usually, it is very useful to use kurtosis to identify the presence of potential outliers. So, and they usually concentrate in the heavier tail sections. And kurtosis, if it's close to a normal distribution, then it's usually equal 3. Whereas if it is a positive kurtosis, this is above 3. So heavier tails in a normal distribution, whereas if it is below 3, we talk about negative kurtosis or lighter tails, so also less chance to find outliers. And I want to show you in this slide how the measure of central tendency, let's say, are related or to a certain extent compared to the shape distribution. We saw that the mean, the median, and the mode, whenever there is a symmetrical distribution, like the one in the middle, you see this very nice bell-shaped, the 3 measures tend to be overlapping. Whereas when we have a left skew distribution, and we say that it is left skew because basically the tail is on the left side, we see that how the mode, the median, and the mean are kind of distributed. Similar when the data are right skewed. And then I want to show you also how different value of kurtosis in the distribution could look like. So the green line indicates the kurtosis equal to 3. So when it's closer to a bell-shaped distribution, you see this very nice, very bell-shaped. And for values that of kurtosis above 3, the blue one, you see this section here, it's much bigger, right? It's much, we say that it has heavier or thicker tails, and therefore it's much more likely that outliers concentrate here. Whenever it's below 3, you see on the other hand that it's rather, everything is rather close, or values are rather close to the mean, so that it's not so likely to have a lot of outliers. And we can use, for example, this measure of shape distribution to answer question, for example, how does the distribution of student test scores look like? And usually, if you remember your time at school, this distribution usually tend to be very symmetrical, where you have most people around the center, so close to the mean, and only very few people that achieve extremely high scores and few that achieve very low scores. Or another question we could answer, in which asset, for example, should I invest if I want to gain a small but secure return? So this means something that is not an outlier, basically, right? So something that is sort of constant over time. Well, in that case, we should probably go for, or we should probably look in a distribution where the data with the kurtosis, for example, is below 3. So much smaller, much thinner tails. Okay, we have so far looked at univariate analysis, so only one variable at a time. What if we want to do bivariate analysis? So basically describing how 2 variables interact with each other. For that, we have so-called measures of association. So they are used to quantify the relationship between 2 or more variables. And typical measures are covariance and correlation, and we're going to have a look at them. So the first one is covariance. Basically, this is a measure of how 2 random variables vary together. So for example, let's say the height of a person and the weight of a person. Usually when height increases, also weight tend to increase. So we can say that they have, they basically have a positive covariance, and they basically vary together. So we are able to tell something about the direction of their relationship. And in fact, covariance can be above 0. So if there is a positive covariance, like I said, imagine on the x-axis we have height, and here we have weight. We can, let's say, generalize by saying that when one increases, the other one increases as well. If we have a negative covariance, the opposite is true. So whenever one variable increases, the other one decreases. And you can think of it, for example, the more products I buy, this is is negatively has a negative covariance to my bank account, right? And the more money I spend, the more products I have, but also the less cash I have in my bank account. Or we can have a covariance of 0, where there is no relationship between the two variables, like the plot in the middle. And this is the formula to calculate the sample covariance. I'm sure you are already familiar with this formula because it is not so different from the one of the variance. So this is covariance, the other one was variance. We'll see in a second how they differ. But you see, again, this is the sum of the difference between the observation and the mean for one variable, and we do the same for the second variable. Okay. And how they do differ? In fact, there is a little difference. Covariance is associated with variance, so it's not completely, let's say, not complete to separate concept. And they both quantify the distribution of the data point around the mean. However, variance assesses how the data is spread, so it is dispersed around the mean for a single variable, whereas covariance explore the direction of the relationship between two variables. So this is the main point of difference. And this is what we can basically answer using covariance. So basically, what is the relationship between a person's educational level and their health, or is a pet ownership associated with living longer, and so on. And the typical answer we can give is that we may observe that the two values of the variables increase, or the values of one variable increase when the value of the other variable increase. So we can only say something about the direction. But what are the problems with using covariance for interpretation? There are a few. The first and the two most important ones is that covariance per se is not bounded to a specific range. So the value can be extremely large and can be influenced by the scale of the data themselves. So if we're talking about, for example, the income of a country, you can think of that one of those variables will be in the millions or billions of euros, right? So the scale of the data or the variable is going to be extremely big. And because covariance is not bounded to a specific range, we might have some difficulty encompassing, like visualizing how the relationship of these two variables is actually described. Another important point, while covariance tells us about the direction, it doesn't tell us anything about the strength of the relationship. So we cannot say if the two variables are strongly related or weakly related. For that, we need correlation. And that's, in fact, the second measure of association we're going to explore. Correlation is, in fact, a function of covariance. But on top of telling us the direction, it also tells us something about the strength of this relationship. And in fact, correlation, very similar to covariance, can be positive, can be negative, or can be 0. So if the two variables are independent from each other. And this is the formula that we can use, for example, to compute correlation. And one of the most popular, let's say, measure is the Pearson correlation coefficient. It is a widely used correlation statistics to measure basically the degree, the strength of the relationship between two linearly related variables. The term linearly here is key because it's one of the, let's say, the main requirement for using this measure. And as you may notice, because we saw that before, these S, X, and SY indicate the sample standard deviation for one variable, for variable X, and for variable Y. The very good point about correlation is that it is bounded in a specific range between -1 and 1, where -1 indicates negative correlation and +1 indicates positive correlation. That's very important. And so this boundary basically helps a lot with interpretation. Here, I leave you this to look at home. It's a basic rule of thumb to understand or to work with correlation coefficients. And these are the questions that we can answer with correlation. Basically, the same one we can answer with covariance, but with the big difference. Now, we not only can see or can say something about the direction of two variables, but also about how they are strongly or weakly, for example, correlated, or whether maybe there is absolutely no correlation because they are independent. And it is important, or it is advantageous to use correlation because it offers some key advantages for interpretation. The first one, and that I already mentioned, is because it is bounded in a specific interval. And also, it tells us exactly the strength of the two variables, and also correlation is not bound to specific units. So while covariance always has specific units, correlation doesn't. So it is sort of just a coefficient, really, that doesn't have any tie to the unit of measurement. And also correlation, because of that, it's also not affected by any changes in the mean or scale in the variables, because it is calculated using the deviations of the two variables with respect to the mean. So it is in a way a bit more robust than the using covariance. But there are other measures of association within correlation. So we see Pearson correlation coefficient, which is the most widely used one, but there are others. For example, Spearman rank correlation. This is a measure of basically the strength of a monotonic association. What does it mean, monotonic association between variables? Basically, they have not only the same direction, but not necessarily the same constant rate of change. So maybe one variable changes faster than the other. And so this measure indicates the strength of monotonic association between two variables that are usually measured on an ordinal or rank scale. And if you can think of, for example, of data obtained from a Likert scale, when you have a survey, so how do you like our service from 1 to 5, that would be a Likert scale, or if data are represented in a hierarchy. And it is also bounded between -1 and 1. So it also offers a very specific range for interpretation. Another measure of association is Pearson's chi-square test. This type of correlation doesn't indicate a measure of strength, but rather a measure of significance. And the big or important point here is that it can be used with categorical variables, so not with numerical ones. So this is extremely interesting because it allows us to, for example, study the relationship between gender, so for male and female, and how that correlate with political party preferences, for example. But important, don't think of correlation or use correlation with attention and guardrails. So correlation, it's not causation. This is a very important point. I'd like to stress it multiple times. If something of two variables have a strong correlation, strong positive correlation, or even negative correlation, that doesn't mean that they are linked by a causal effect relationship. So, for example, we can say that smoking is correlated with alcoholism, but it doesn't cause alcoholism. So that's a key difference between two variables that are correlated and two variables that are basically one the effect or the cause of the other. And also, important as correlation can be found in many different variables, but the relationship can be actually due or explained by many other different factors. In fact, there is a popular website where you can explore many different random positive correlation, and one is, for example, that UFO sightseeing in Florida and the popularity of the name Camden. You see there is absolutely no rationale or meaning in this correlation, and yet those variables are positively correlated. So please be careful when you use this measure because correlation doesn't automatically imply causation. Okay, and with that, I would like to then spend a few more words on how you can use descriptive statistics not only to summarize your data, which is what we had just seen, but also how to present your data. And for that, we usually use visualization, so data visualization techniques, and each visualization technique tend to be appropriate for a specific data type or to display specific information or relationship. And some of the typical plots that we use to present our data are the bar chart, the histogram, the density plot, the box plot, and the scatter plot. And we're now going to have a look at each of them in a little bit more detail. The first one, and probably one that you have seen, I'm sure you've seen somewhere or before, is the bar chart. The bar chart summarizes some categorical data. It's usually good or useful to plot or spot differences between two or more categorical values. And on the horizontal axis, you usually have categories, whereas on the y-axis, you usually have some metrics. So it can be the average, it can be the count, it can be the sum, and so on. And it also can be used to, for example, display groups or display stacked groups. So it's a very powerful plot. And one that looks similar to the bar chart, but it has completely different use, is the histogram. Histogram also are useful to, let's say, to represent our data, but they summarize usually measurement data. And they do so by dividing each, let's say, basically each data into groups, into equally sized groups that we call bins. It's used to represent a single numerical column. And on the horizontal axis, we tend to have the range, so basically our bins, like you see here. And on the y-axis, we usually have frequency. So how many items, how many observations are included in a specific bin. Yeah, and it's of course how to define the bins. This can be either a trial and error procedure, or you can also refer to specific literature for a specific variable that you're trying to represent. Another one that is not so different from the histogram is the density plot. This also summarizes measurement data. It's also useful to basically to plot the distribution of one numeric column, and it's sort of a smooth version of the histogram. And what is interesting that it tells us how the probability, basically, that some specific outcome will occur. So in the plot that we have here, we are representing on the horizontal axis, we are representing the age. So for example, we can say that a person whose age is roughly almost 31 years old, the probability that to observe this outcome is roughly 0.026. That's what the plot tells us. The next one is the box plot. The box plot also summarizes measurement data, and it's useful because it tells us a lot of information. It tells us how spread the data is, how symmetric it is, but also allow us to identify outliers. Here in the plot, you see there are these little points here. Those would be our outliers. So basically, data points that are distant from our let's say typical observations. And usually our horizontal axis represent the categories, whereas the vertical axis represent the measurement data. And it's also very good to compare multiple groups. So here, for example, on the plot, we have the number of years of education, but we could have also, for example, the salary and I don't know, the age and so on. And it's also important or interesting to notice that this our arms here are called whiskers, and they extend up to the most extreme point in the distribution, so in our data set. In fact, you can see in this little tooltip that the minimum value here is 4.5, and the maximum value is 16. And below or above that, we do find outliers. And the last of our plots is the scatter plot. The scatter plot is very useful if we want to summarize or visualize the relationship between two numeric columns. Also in this case, we basically each axis represents one of the two variables, and obviously each point, let's say each dot on the scatter plot represents one observation from the two variables. And it's also very useful to identify, for example, outliers, but also imagine the relationship between two variables. So we, in fact, often use this plot to represent how two variables are correlated, if they are at all correlated, right? So in this case, for example, you see there doesn't seem to be a clear correlation between the number of education years and the age. Okay. And now let me spend a few words about how you can do statistics with KNIME. KNIME is the tool that we will use today to perform and to do some calculation in that sense. For those who are not familiar with KNIME, KNIME is a tool for data analysis and data science, data engineering. So it has many different applications. And with this tool, you can do transformation, visualization, or reporting on your data. It is open source, and it doesn't require coding to be used. So you can actually use a visual programming paradigm. So no coding needed, but code can be integrated, and you can access NIME Analytics platform via the BTDI service offering. So it's already there for you to use. NIME uses the concept of nodes to perform tasks on the data. So each block, what you see here, this, for example, this yellow block is a node. And as you can tell from the name, what it does in this specific case, it splits the table into different partitions. The node usually takes some inputs. So you see this inputs data goes here, and output or outputs goes out. And also has a traffic light here to indicate the status of the node. So if it's red, then it's not configured. If it's yellow, the node has been configured. And it's green, for example, then it's been configured and executed. If there is an error, so this little X, then something probably didn't go right with the configuration of our node. Now, when we combine nodes, we connect nodes sequentially one after the other, we create a so-called workflow. So what you see in the lower part of the slide, that is a workflow. So a collection and of nodes that are connected sequentially one after the other. And workflow can be very simple, for example, like the one you see here for some basic ETL process, or very complicated if you want to train, for example, some machine learning model to obtain some predictions. And NIME, you have many different nodes and extension to work with statistics. So we have the NIME statistics node, if you want to, for example, identify outliers or run some simple hypothesis testing, or, for example, compute the correlation. Then we have a different extension called NIME Statistics Nodes Labs, in case you want to do more advanced hypothesis testing. So those are, let's say, nodes are used usually for inference statistics, where we saw at the very beginning. And then we have different visualization nodes. They usually designed, or they're usually marked in blue, that are, for example, allow us to basically create bar charts, histogram, boxplot, and so on. And all of them, they are all accessible through the BDTI service offering. So you just good to go and use them. How can we perform now descriptive statistics with NIME, especially for univariate analysis? So remember, these were the mean, the median, the standard deviation, all these measures. We can do this with only one node. Here I show 3 and explain you why. We have, so these 3 nodes vary, or the use of it vary according to what in this scenario we need to use them. So we can have the data explorer, the first one, if we want to have statistics and histogram visible in an interactive dashboard, but we are not interested in actually having the measure, so the statistics at the output port. We don't want that. We just want to have them visualized in an interactive dashboard. Then, in this case, use the data explorer. If you want to use a different one, for example, the statistics node, this is not compatible really with interactive dashboard, but it offers at the output port the statistics table, the nominal histogram, and also a table of occurrences of your variables. And the third one, the statistics view, it just offers a view of the statistics. It is compatible with dashboards or with interactive dashboards, but it doesn't offer any output table. So it really depends a little bit on what you're interested in and what your use case is. But the point is that this one or this node, depending on which one you need, basically computes all the measures that you need. And that's more or less how the output of these 3 nodes will look like, depending on the scenario you are interested in. Now, on top of these nodes, we can compute more summary statistics using, for example, the group by, the pivot, and the column aggregator nodes. This node originally are used for aggregations, but they have many aggregation measures. And for example, we can use them to compute the mode, to compute the geometric mean, to compute the range, the quantile, and so on. So we have many different additional measures that we can compute using these nodes in our data. And of course, different summary statistics depend on the data type. So we won't be able to compute the mean on nominal data, but we can compute, for example, the mode. And for bivariate analysis, on the other hand, we have node to compute. We can compute the covariance with the group by, the pivot, or the column aggregator node. And if we want to compute linear correlation or rank correlation, we have the dedicated node for that. It's very simple to use, and they will return also not only tables but also correlation metrics. And that's the one you see actually on the slide here. So it's very informative and very nice to visualize. When it comes to visualizations, also in this case, we have many different visualization nodes. Most of them are native nodes. So here I report some of them, the box plot, the scatter plot, the histogram, and so on. But we also have out-of-the-box plots that are integrated with the Plotly extension. And this would be, for example, the violin plot, the arrow bars plot, or the continuous arrow plot. So there are many different ones. And if you really need to use a specific library or a specific package or something that you don't find out of the box, no worries. You can integrate scripting languages with KNIME, for example, the Python integration or the R integration. And especially for the Python integration, the scripting node have an AI assistant to help you code if you need it, or if you prefer to run the specific part of your analysis on another tool. The BTDI framework also has access to Jupyter Notebook or RStudio. So you are very much covered in all your analytic needs for statistics. And with that, I would like to briefly describe what is the little use case for descriptive statistics for today. And that's about crime records. The task in this specific, let's say, little case is to understand some crime numbers using descriptive statistics to basically make sense of those numbers that are reported every year by the police on different crimes for a selected country in Europe. And the idea is to use not only summary statistics, but also visualization to uncover some interesting pattern. The data is sourced from Eurostat. It accounts for annual number of committed crimes reported by the police by crime type. It is available every year from 2008 until 2022. And as I said, it is available from Eurostat. And this is more or less how the workflow looks like. So you have initial access to, the data. For the specific use case, we have access only data from 2012 until 2022. And we initially do a little bit of preprocessing to actually be able to import the Excel sheet into KNIME, and then to select a country we want to analyze. In this particular example, since I'm Italian, I'm just choosing Italy, just because I like the idea. But of course, you are free to choose any country you are interested in. And we then compute some univariate summary statistics, some bivariate statistics. So for example, correlation, covariance, and rank correlation. And then we visualize some feature of our data set to understand it better and to uncover potentially new different type of information. And with this, let me just quickly move to KNIME. And now we're going to make it a little bit bigger so you're able to see my analytics platform. So as I said, we initially read our data. So you see here we have information about different type of crimes for different countries in Europe. So you see it here. And here, as I said, I am selecting just Italy, just because I'm interested in this country from 2012 until 2022. How we compute univariate analysis, so basically summary statistics, we can use either of this node. I will just show this one, which is the Data Explorer. You can see it's quite nice. I have a measure of everything. So I have the mean, the median, the maximum value, the standard deviation. And I can also, for example, do this and immediately visualize a little histogram of the data, or check another one, and so on. So I can have in one node a full picture of basically my data set. And interestingly, we can see, for example, that some of these variables have let's say have some missing value. For example, here there are 7 missing value. Here there are 4. Here there are 5, and so on. So at just one glance, we have a full summary of our data set. And then we can also use the group by node to compute the mode. In this case, because we have so many different numeric values, we don't have a specific mode. I remember that I mentioned that if there is a continuous variable, so a numeric variable with different value, we cannot identify the mode. So the node in this case returns just the first row. And we also can have a compute the range, again, using the group by node. So for example, for sum, I selected just some variables, and we can see, for example, the difference between the highest and the smallest value. Now, since we realize there are some missing values in our data set, we can finally do something about those missing value. And because I know the median is less prone or less sensitive to outliers, I can use, for example, the median, right? And so here let me take a step back. Here, for example, you see those. Let me open it here, maybe it's better. In 9, missing values are identified by those red question marks. And you see, for example, the variable sexual violence or sexual exploitation have some missing values, and therefore I can decide to basically handle those missing values, and I decide to fill them up with the median, right? So now you see no more red question marks. At this point, I can calculate, for example, the covariance, and I can do that with the group by node again. And here I'm just choosing just 3 set of variables, and you can see here that those values are extremely high. We're talking about in the range of millions, right? So this is one of the problems I was mentioning. Covariance is not bounded, and we know, for example, that there is a positive covariance, so they are one variable varies, the other one varies as well, but it is a very high value, and it makes it extremely hard for interpretation. So what can we do instead? We can use correlation. We can use, for example, linear correlation if we are assuming that these two, the variables are linearly correlated, and we can see, for example, that there tend to be a strong linear and positive correlation between intentional homicide and attempted intentional homicide, or intentional homicide and serious assault. So they are all above, they're all approaching, let's say, 1. But what if our variable are not linearly, there's no linear relationship? Well, in this case, probably using a rank correlation is much better, because this requirement is not needed for Spearman rank correlation. In fact, it is the case that intentional homicide and serious assault now has a much higher correlation value, and this tells us that probably these two variables, they don't vary at the constant rate. So they are not linear, but rather there might be a monotonic relationship. So this is one case where using or checking both correlation values could be useful. And now we want to, for example, also check some of the plots. And if we check the histogram plot, we can see for intentional homicide that we have this little peak here and this little peak here. And if you check the range of the bins, you can see that there is four items in the first bin and 3 more items in the last bin. This seems to tell us that there are basically two main groups, 2 main modes, and therefore we might be looking at a sort of B-model shape. In fact, if we now check the density plot, in this case we check the one for Italy in blue, and also we include another country for comparison, in this case France, you see this shape is more or less what we saw in the histogram for the variable intentional homicide. So we can see basically how the shape is looking, and it's very intuitive, and we also can understand that probably there was a higher number of intentional homicide reported in some years, and then a sort of drop in later years. Whereas in France, for example, there seems to be a much more like bell-shaped distribution, so a more normal distribution in that sense. We can also, for example, check the box plot. In that case, we'll see different type of information. So we see that for the variable sexual violence for Italy, which is in green, we have one outlier here. So we know that there is this value, this 783, seems to be rather an outlier value for Italy. And also we can see here in the case of fraud that the data is much more spread, right? You see that the median, which is this line, this little line in between, is rather close to the first quartile. So you can see that it seems to be a rather spread distribution of our data. And lastly, I will show you the scatter plot. Here we are trying to understand whether there is some sort of relationship between the variable fraud and versus acts against computer system for countries like Italy and France. And here we see France with orange and Italy with blue. And you can see that the data seems to show a very strong positive correlation. So basically most acts against computer system tend to be correlated or positively correlated, strongly correlated with fraud. So it is a fair assumption to make that maybe if there is a hack of a system, a computer system, this is because there is some fraudulent intent behind it. Okay, with this being said, let me go back to slides and let's introduce now our second topic, which is that of probability. Probability, what is this? Let's first define it, is a mathematical way of describing how likely or unlikely a specific event it is to occur or not to occur. And usually probabilities are expressed in fractions, decimal number, or percentages, and are values bounded between 0 and 1. So again, this is super important because it allows us for an easy way to interpret our results. And the probability is used in many real-life scenarios to predict, for example, the outcome of an event. Typical probability we usually want to calculate is how likely it is to become or to win the lottery, right? So we all would like to know this. So this is one specific use case, but it can also be used to calculate the probability of a specific weather condition to happen. So how likely it is to be rainy tomorrow or sunny and so on. And important, let's define also some key terms also in this case when we talk about probability. The first term we want to define is the term experiment. So this is an activity where we do not know for certain what will happen, but we do have the option to observe the outcome. So for example, we roll a die and we by doing this, we can observe what outcome it gives us. So basically we have the option to run an experiment and observe the outcome. And in fact, the second term is specifically outcome. That is one of the possible things that can happen, for example, when rolling a die. And the third one is event. That is a particular collection of outcomes that can be observed within an experiment. So if we roll, for example, a die for an even number, in this event, there are 3 possible outcomes. That is, the die can give us a 2, a 4, or a 6. Now, if we want to understand probability, let's think also of what happens when we toss a fair coin, right? Fair coin, it is important that a coin needs to be fair because it means that it has a head and a tail. So when we toss a coin, the probability of getting a head or a tail is basically the same, right? So it's 50%. And in fact, the probability of head is 1/2. The probability of a tail is 1/2. And with this formula, so the number of outcomes in event over the total number of possible outcomes, we can compute very simple probability. So if we say that an event is, or that an outcome has the 50% probability of happening, this means that either of the two events can happen or not happen in with the same likelihood. But also, events or outcomes not only have 50% probability. Usually, in fact, we can have events that have a 0 probability if it's an impossible event, or 1 as a probability. So if the event is certain. Let's say probability of the Earth being flat is 0, whereas the probability of tomorrow being Thursday, if today is Wednesday, is 1. Very simple. And important, event cannot be less likely than impossible, obviously, or more likely than certain. Now, when we compute probability, we also need to keep in mind what kind of events we are looking at, because depending on the events, also the calculation of probability changes. And we're going to have a look at 3 different events: mutually exclusive events, non-mutually exclusive events, and independent events. Let's first have a look at mutually exclusive events. Those are events, for example, event A or event B, that cannot happen at the same time or simultaneously. And a typical example here is either you win or you lose a game. So you cannot win and lose at the same time. And in these cases, we can compute the probability of event A or event B to occur by summing up the individual probabilities of each event. So for example, the probability of event A or event B to happen is just the sum of the probability of A and the probability of B. And I'm just using here also some set images because that's a very typical way of representing probability in textbooks. And important, we can also, instead of using or, we can also use the symbol U, so that stands for union, which is also a different way of writing, so the different notation that you can find in textbooks. Now, if we want to have, for example, if you think of to visualize these mutually exclusive events, think of a fair die and calculating the probability that the dice show a 2 or a 5. So the probability of getting a 2 is 1 over 6, right? And the probability of getting a 5 is 1 over 6. So the probability of getting a 2 or a 5 is obviously the sum of these 2 probabilities. Very simple. Now, what happens when the things get a little bit more complex when we talk about non-mutually exclusive events? Those are events that can happen at the same time, so simultaneously. And for example, here, the typical, example in real life that you can think of, there is a probability that you can have a cold and a headache at the same time. Now, for non-mutually exclusive events, we can also compute the probability. And in this case, we need to have a little bit more complex, let's say, calculation. That is, we want to understand or calculate the probability of event A or B as the sum of each probability of A and B minus the probability of A and B happening together. And let's look at the set here in the image to have it a bit more clear. So A is basically the probability of event A, and B is the probability of event B. What we are interested in is basically the white sections of both sets. So we sum the probability of A, we sum the probability of V or B, but we need to remove the intersection of these 2 sets. Otherwise, if we don't remove it, we are basically computing the same event twice. So we're basically obtaining a fake or a wrong probability calculation. Also in this case, mind that this formula can be written in a different way. So using the sort of upside down U, which stands for intersection symbol. So we could write the third term in the formula as a probability of A intersection B. And here, a typical example would be, for example, that of using a standard deck of French cards. And let's say we want to compute the probability of picking a card that is a hearts and a queens together, right? So basically for this to happen, for this phenomenon to happen, we basically are looking for the queen of hearts. And so, okay, so let's calculate, first of all, the probability of finding the queen. We know there's only 4 in the deck, so it's 4 over 52. And probability of heart is 13 over 52 because there are 13 heart cards. Now, if we would stop here, like I said, we would count queen and heart twice. So we need to correct that to basically have the correct calculation. So we need, therefore, to calculate the probability that we have a queen and a heart at the same time. So basically the probability of finding the queen of hearts, which is only 1 in the data set. So 1 over 52. At this point, we bring it all together, and therefore the probability of finding a queen or heart, it is just 30.7%. So we sum the probability of queen We sum the probability of heart, and we subtract basically the intersection of queen and heart. The last type of events I want to talk about are independent events. Those are events whose occurrence does not depend on any other events. And for example, here we can roll a die or pick a card from a deck, and these two events are completely independent from each other, so they are not influencing each other in the outcome. And so how can we compute the probability for independent events? In this case, it's very simple. We just apply a multiplication. So the probability of event A times the probability of event B. Here, the example is how we can calculate the probability of rolling a die that gives us 2 or a value that is below 2 and drawing a card of hearts. So the probability of rolling a die with a value of 2 or less is 2.2 over 6, because it can be 1 or can be 2, times the probability of basically picking a card of hearts, which is only 13, because only 13 cards have hearts, so 13 over 52, and then the multiplication is 1 over 12. That's how we can compute the probability of independent events. However, most likely, when we observe social phenomena, we are not observing independent events from each other. Usually, when we want to create some probability or calculate some probability for phenomena that we're interested in, usually there is some level of dependence. And therefore, we need to introduce a different way of computing probability. And with that, we introduce the concept of conditional probability. This conditional probability measures the probability that an event occur given that another event has occurred before. So we need to calculate something given that something else has already happened. And we can denote this with this little, let's say, notation, where probability of B, so the event we were interested in, given that A has already happened. And this has a formula that we need to use, so we need to compute conditional probability whenever we have events that are not independent. And so how can we compute this probability? Basically, by multiplying the probability of A times the conditional probability itself. And a typical example again is that, let me pick again the cards, the French deck cards. And in this case, you want to compute the probability of drawing 2 kings one after another. So you see there is some dependence of events, because obviously once we pick 1 king, the number of kings left are decreasing. So event A is picking 1 king first, and event B is drawing a 2nd king. So in the first case, we have 4 over 52. So we have 4 kings out of 52 cards. But in the second event, we don't have the same amount of kings. So picking again a king becomes less likely. So the probability of picking a king, so probability, this part here, probability of picking a king, given that already a king has been picked, is now 3 over 51. So if we want to compute the probability of picking 2 kings in a row, we need to multiply the probability of picking a king times the probability of picking a king, given that already a king has been taken out from our card deck. And that's about 0.5%. And if we use algebra, we can transform a little bit this formula to look like this. So we can have a very nice formula that we can apply straight away to our computation of conditional probability. So the probability of A and B over the probability of event A. In real life also, consider that not only we tend to observe the events that are rather dependent from each other, but also we learn from past events. So whenever we learn from past events, we can introduce this new learning of events or this update of information that we know about the world to change or to modify the way we calculate probability. So for example, how can we update our probability calculation if we now have new information about how likely it is for an event to occur? Well, for that, we need to introduce the so-called Bayes Theorem. So it is a way of finding a probability when we know that certain other probability can occur. And a typical scenario where this is used is, for example, the financial sector, where they update the probability of of a risky stock because they know how likely or how unlikely it is for an event to occur, because they simply have historical data about what happened in the previous days or weeks. And the computation of the formula with Bayes' theorem is rather simple, and in fact, it doesn't introduce terms that are completely new to us, right? We already seen the probability of event A, for event B, and the conditional probability term. But let's be clear about what about single event means. So the probability of A given B tells us how often A is likely to happen given that B happens already. And this is called, in general, posterior probability. That's what we want to get, right? What we want to know. Then we have the probability of B given A has happened, which is the likelihood. And then we have the probability of A, which is the prior probability. That's what we know today about how likely it is for an event to happen. And probability of B is basically how likely event B is to happen. And with that information, we can, for example, just to give you a clear understanding, we want to know whether we should be going sailing on a morning that is cloudy. What we know is that, for example, this month is rather dry, so there is a probability of raining that is only 10%. Whereas we also know that 50% of all rainy days, so the probability that the day is rainy given that it's cloudy, is around 50%. And we also know that cloudy mornings are rather common, so this happens with a 40% of chances. At this point, with these three percentages, we just want to answer the question, what is the chance that a rainy day, that rains during the day when we are planning to go sailing? If we plug this value into our formula, we obtain that basically there is 12.5% of chance of raining, and therefore it's probably safe to go sailing. How we can compute probabilities with KNIME? We have the option mostly to use the math formula or the pivot node if we want to have compute some specific groups or compute some specific, let's say, ratios. And the important point is we don't have a specific, let's say, node to compute probability out of the box. And there is for a reason, mostly because probability computation, so calculation of probability usually answers a specific question from the user on specific data. So it's really handcrafted in a sense to answer the specific question you may have. So that's why the math formula is in fact the most powerful tool to calculate probability in KNIME list. And so to show how you can do this in KNIME, we use the so-called employment survey. This is also in this specific case we want to understand. I want to use the employment survey data about a specific country to compute different probabilities for a specific demographics. That is, males in the age group between 50 and 24. And then we're going to use probability to calculate, for example, the probability for mutually exclusive events, non-mutually exclusive events, conditional probability, and Bayes theorem. The data is employment survey data. Those are calculated, those are annually recorded data, and by population age, groups, and sex. Also sourced from Eurostat, and they cover a period span that goes from 2003 until 2023. And this is more or less how the workflow looks like for this 4 type of calculations. So we initially access the data, this only for the year 2023, again for a specific country, but you can choose the country you like. I chose again Italy, and after that we can compute probability for mutually and non-mutually exclusive events. And third step is to compute probability for conditional probability, and the fourth one is to compute probability using Bayes theorem. And for that, I will quickly move to KNIME, and then I wrap it up so we can go to the questions. This is how the workflow will look like. I'll make it a little bit bigger so you can see. You find all this material anyway available, so you can go through it at your own pace again. So imagine, for example, for the mutually exclusive events, we want to understand what's the probability, for example, for an employee in Italy to belong to the age group of 15-24 or 25 and 54. So obviously, a person cannot belong to two different age groups at the same time, right? So for this reason, they are mutually exclusive events. And once we access our data, which is how they look like, so basically you have so the total of, so for the column sex, you have totals, males and females, different age classes, so from 15 to 24, from 25 to 54, and from 55 to 64 for the year of 23, and the number of, basically the count of thousands of people. So we start obviously by retaining just the age group that we're interested in. So, and then we sum the total employees. So you can see here, and basically we sum how many people in total are employed in Italy. In this case, we have about 22 millions. And at this point, we can compute finally the probability. And remember, in this case, the probability was just the sum of two different probabilities. So you can see in the math formula, sorry, before that, we need to first compute the probability for each age group. So then the number of people in each age group over the entire amount of employee in Italy. And after that, we retain only the group of interest. So basically the 15 and 24 and 25 and 54. Those are the two age groups that we are interested in. And only here, finally, we can sum those two probabilities. So you can see here, we basically just sum the two probabilities and multiply by 100. So we obtain the probability of a person to belong to either of the groups, age groups, is 77.6. Now, for non-mutually exclusive events, the calculation is a bit more complex because we need to account for the intersection of the people in the age of 15 and a male. So here the question is, what's the probability of an adult employee to be either from the age group 15 to 24 and being male? So of course, again, we need to first calculate the probability of belonging to a specific age group. So, and that's what we have here. So actually, this has already been computed from the previous step. So we can simply filter the age group we are interested in. So it's here. We're only basically interested in this age group. And we basically, with the math formula, compute the ratio between the number of people employed in the age group 15 to 24 over the entire amount of people in the category. Then for male, so to the second probability, we need to compute is that of male. Then to compute this, we first sum the number of males in our data set. And to compute the probability, again, we also need to calculate basically, again, the ratio of males over the entire amount of employees in Italy. And we get basically this probability, which is 0.573. The last part involves the calculation of the probability of belonging to the age group 15 to 24 and being male. And this is also something that we can compute, again, basically by providing a ratio. And lastly, we bring everything together. So we append all this calculation together. And with the math formula, we just apply the formula that you see here in the annotation. We basically, the probability of belonging to one age group, the probability of being male, and the difference between the two probabilities. And just for the interest of time, I'm just going to cover now only the conditional probability here in the workflow. But the idea is pretty much the same. In the conditional probability, we want to, in this case, calculate what's the probability of an employee in Italy of being male, given the condition that this person also belongs to the category group, to the age group 15 to 24. This into information, we are very lucky because we already have computed them before. So we simply extract the cell for this probability of being male and being 15 to 24, and the probability of belonging to the group of 15 to 24 years old. And here, what we only do is simply this ratio. So we divide the two probabilities and obtain the conditional probability of being a male, given that the person belongs to this age group, is 16.64%. And with that, you can modify and, let's say, customize the computation of your probability to your specific needs. To recap and to sum up what we have learned today, we've seen some key concepts in statistics and measure for descriptive statistics, and also how to present your data with visualizations. We also have introduced some very basic concept of probability and how you can compute these probabilities for different event types. And lastly, we have seen how we can compute some of those descriptive statistics or probability using NAM Analytics platform. You find all this material, all the slides and the code and the workflows available on the BTDI Skills Studio GitHub repository and at this link, and you can also access via the QR code. And with that being said, I apologize for taking a little bit more time than needed, but I'm happy now to answer your questions. Let's see if there is any question here. I don't seem to see any, but maybe I am not seeing it correctly.
Hi, Roberto. Yes.
Yes.
So first of all, thanks a lot for this amazing intensive learning session, I would say.
Yes, it was intense.
Maybe people are still trying to digest the content. So I don't see any question in the Q&A, so please don't be shy. You can also ask question that sounds to you a bit stupid, no stupid question first. Second, I have a question from my side, just to maybe understand a little bit more about what you mentioned at the beginning. So when you were presenting random sampling,
Mm-hmm. Yes.
One of our questions is, what are other sampling strategies, and when would be useful to not have random sampling?
Yes. For example, one very popular other option is stratified sampling. What does it mean to have a stratified sampling? So imagine you want to make sure that a specific type or a specific variable is absolutely represented in your sample. Now, when you use simple random sampling, maybe I can go back quickly to the very initial slide. We said that one of the requirements for that, sorry, this is a bit at the beginning, is that that every single item in the population has the same chance to be selected. Now, it also be the case that whatever your specific interest doesn't get selected, right? So when you do this procedure, you don't get the information that you want to. So how can you kind of correct that error, or let's say that sort of error, by using, for example, stratified sampling? Here, you enforce that one specific feature or column has to be represented, and then you basically sample data, given that that category is always there. You can also have, for example, cluster sampling. In that case, you use basically a cluster approach, so to group data into different category, into different groups really, and then you sample from each group a few elements, a few data points using simple random sampling. So those are two options that you can have to have something different, to have a different approach, more sophisticated, in fact, than simple random sampling. The point is, however, in both cases, that you want to make sure that your data you get, or your sample, is a fair and unbiased representation of the population, because this is the only way you can then make inference, you can then make or compute statistics about it, so that in the end your summary statistics or your visualizations, your probability calculation are actually meaningful. Otherwise, you might just be biased toward one direction or the other.
Thanks a lot, Roberto. Before closing, there is still one question in the chat. It's a bit generic, I would say. So the question is, in the context of public procurement using CIG system and NIME, what are some innovative approaches to identifying and addressing biases in data and models? I would say that we can try to reframe the question in general. Which are the best, maybe the best tools, if any, in NIME to identify quickly some biases and also some, weird maybe outliers in the data set, I would say, because
yes. So if we want to identify, for example, some outliers, we do have a specific node that is again, I need to go back and forth the slides, but it's already shown in one of the slides, so I can quickly pick it for you. So yes, here. So you see in the slide there is this numeric outlier detection node. This one and this one, they are basically doing the same. And here you can immediately handle outliers in numeric columns. So this is a very useful way to immediately identify outliers in your data set and decide to do something about it. Now, if you want to, for example, detect the potential of bias of different types, so maybe there is some misrepresentations or some other type of bias, usually you can do that, for example, specifically if you are training, let's say, a machine learning model, we have a so-called GIScard node. So the GIScard is a framework that allows, so it's an extension for NIME. So again, this is also available in the BTDI framework because it's a NIME extension. And you can, you basically obtain a report of your machine learning pipeline that identifies all potential risk and vulnerability, including, for example, bias. Or you do, for example, hypothesis testing, and you can understand, okay, maybe the claim about a specific value of the mean amount of my data is not really holding. So if your hypothesis is not, let's say, cannot be verified or is rejected, then you know that probably your assumption is not right in the first place.
Thanks a lot, Roberto. Yeah, but by the way, just for the participant, we want to remind you that in the GitLab repository, you will find also some interesting learning resources, some books from academia, where all these concepts are very well explained using also Python and R. No problem. So if I'm not wrong, I don't see any other question
I want to go back to the last slide so you can maybe... Apologies. Yes, here's what we've learned. Yes, here and there. Sorry. Yeah.
Okay, cool. So just to remind you that we still have, I would say, a lot of interesting webinars for the next weeks. The next one is about graph analytics, a very, very relevant topic, even more in the public sector when it's about try to understand and create knowledge, for example, using let's say linked data approaches and in general graph analytics tools. So I will strongly recommend you subscribe to this webinar and also check the other dates when we are going to define different use cases using open data from, for example, from transportation, from smart cities. Then if we go to the next slide, we just want to wrap up also the main idea behind BDTI. What we learned today with Roberto is something you can really try to, let's say, experiment with your data, maybe your data set that you're producing in your municipality or in your region. You have this platform that's free. You just need to apply submitting a nice pilot, a nice idea. So again, don't hesitate, check our website. You have also our functional mailbox. And then if you go to the last slide, you have all the QR codes with all the resources. Also visit our section, let's say the service catalog section. You have all the tools. You have already a nice BDTI essential training with another use case we developed together with Roberto colleagues. And then we have an amazing newsletter where you can stay up to date with our initiative. So thanks again, colleagues. Thanks a lot, Roberto, for this, I would say, academic lecture. And see you soon in the next week. Thank you.